Let's talk about another kind of neural network, the recurrent neural network. What are RNNs for? Well, a couple of things. Basically, they're for sequences of data, and that might be a sequence in time. So you might use it for processing time series data, where you're trying to look at a sequence of data points over time and predict the future behavior of something over time in turn. So RNNs are based for sequential data of some sort. And some examples of time series data might be web logs, where you're receiving different hits to your website over time, or sensor logs, where you're getting different inputs from sensors from the Internet of Things. Or maybe you're trying to predict stock behavior by looking at historical stock trading information. These are all potential applications for recurrent neural networks because they can take a look at the behavior over time and try to take that behavior into account when it makes future projections. Another example might be if you're trying to develop a self-driving car. You might have a history of where your car has been, its past trajectories, and maybe that can inform how your car might want to turn in the future. So you might take into account the fact that your car has been turning along a curve to predict that perhaps it should continue to drive along a curve until the road straightens out. And another example, it doesn't have to just be time. It can be any kind of sequence of arbitrary length. So something else that comes to mind are languages, sentences. They're just sequences of words, right? So you can also apply RNNs to language or machine translation or producing captions for videos or images. These are examples of where the order of words in a sentence might matter, and the structure of the sentence and how these words are put together could convey more meaning than you could get by just looking at those words individually without context. So again, an RNN can make use of that ordering of the words and try to use that as part of its model. Another interesting application of RNNs is machine-generated music. You can also think of music sort of like text, where instead of a sequence of words or letters, you have a sequence of musical notes. So it's kind of interesting. You can actually build a neural network that can take an existing piece of music and sort of extend upon it by using a recurrent neural network to try to learn the patterns that were aesthetically pleasing to the music in the past. Conceptually, this is what a single recurrent neuron looks like in terms of a model. So it looks a lot like an artificial neuron that we've looked at before. The big difference is this little loop here. Okay, so now as we run a training step on this neuron, some training data gets fed into it, or maybe this is an input from a previous layer in our neural network, and it will apply some sort of step function after summing all the inputs into it. In this case, we're going to be drawing something more like a hyperbolic tangent because mathematically we want to make sure that we preserve some of the information coming in more of a smooth manner. Now, usually we would just output the result of that summation and that activation function as the output of this neuron, but we're also going to feed that back into the same neuron. So the next time we run some data through this neuron, that data from the previous run also gets summed in to the results. Okay, so as we keep running this thing over and over again, we'll have some new data coming in that gets blended together with the output from the previous run through this neuron, and that just keeps happening over and over and over again. So you can see that over time, the past behavior of this neuron influences its future behavior, and it influences how it learns. Another way of thinking about this is by unrolling it in time. So what this diagram shows is the same single neuron, just at 3 different time steps. And when you start to dig into the mathematics of how RNNs work, this is a more useful way of thinking about it. So if we consider this to be time step 0, you can see there's some sort of data input coming into this recurrent neuron, and that will produce some sort of output after going through its activation function. And that output also gets fed into the next time step. So if this is time step 1 with this same neuron, you can see that this neuron is receiving not only a new input, but also the output from the previous time step. And those get summed together, the activation function gets applied to it, and that gets output as well. And the output of that combination then gets fed onto the next time step, called as time step 2, where a new input for time step 2 gets fed into this neuron, and the output from the previous step also gets fed in. They get summed together, the activation function is run, and we have a new output. This is called a memory cell because it does maintain memory of its previous outputs over time. And you can see that even though it's getting summed together at each time step, over time those earlier behaviors kind of get diluted, right? So, we're adding in that time step to that time step, and then the sum of those two things end up working into this one. So one property of memory cells is that more recent behavior tends to have more of an influence on the current behavior that you get out of a recurrent neuron. And this can be a problem in some applications. So there are ways to work against that we can talk about later. Stepping this up, you can have a layer of recurrent neurons, so you don't have to have just one, obviously. So in this diagram, we are looking at 4 individual recurrent neurons that are working together as part of a layer. And you can have some input going into this layer as a whole that gets fed into these 4 different recurrent neurons, and then the output of those neurons can then get fed back to the next step to every neuron in that layer. So all we're doing is scaling this out horizontally. So instead of a single recurrent neuron, we have a layer of 4 recurrent neurons in this example, where all of the output of those neurons is feeding in to the behavior of those neurons in the next learning step. Okay? So you can scale this out to have more than one neuron and learn more complicated patterns as a result. RNNs open up a wide range of possibilities because now we have the ability to deal not just with vectors of information, static snapshots of some sort of a state, we can also deal with sequences of data as well. So there are 4 different combinations here that you can deal with. We can deal with sequence-to-sequence neural networks. If we have the input is a time series or some sort of sequence of data, we can also have an output that is a time series or some sequence of data as well. So if you're trying to predict stock prices in the future based on historical trades, that might be an example of sequence-to-sequence topology. We can also mix and match sequences with the older vector static states that we predicted back with just using multi-layer perceptrons. We would call that a sequence-to-vector. So if we were starting with a sequence of data, we could produce just a snapshot of some state as a result of analyzing that sequence. An example might be looking at the sequence of words in a sentence to produce some idea of the sentiment that that sentence conveys. And we'll actually look at that in an example shortly. You can go the other way around too. You can go from a vector to a sequence. So an example of that would be taking an image, which is a static vector of information, and then producing a sequence from that vector, for example, words in a sentence, creating a caption from an image. And we can chain these things together in interesting ways as well. We can have encoders and decoders built up that feed into each other. For example, we might start with a sequence of information from a sentence of some language, embody what that sentence means as some sort of a vector representation, and then turn that around into a new sequence of words in some other language. So that might be how a machine translation system could work, for example. You might start with a sequence of words in French, build up a vector that sort of embodies the meaning of that sentence, and then produce a new sequence of words in English or whatever language you want. That's an example of using a recurrent neural network for machine translation. So lots of exciting possibilities here. Training RNNs, just like CNNs, is hard. In some ways, it's even harder. The main twist here is that we need to backpropagate not only through the neural network itself and all of its layers, but also through time. And at a practical standpoint, every one of those time steps ends up looking like another layer in our neural network while we're trying to train our neural network. And those time steps can add up fast. So over time, we end up with like an even deeper and deeper neural network that we need to train. And the cost of actually performing gradient descent on that increasingly deep neural network becomes increasingly large. So to put an upper cap on that training time, often we limit the backpropagation to a limited number of time steps. We call this truncated backpropagation through time. So just something to keep in mind when you're training an RNN, you not only need to backpropagate through the neural network topology that you've created, you also need to backpropagate through all the time steps that you've built up to that point. Now, we talked earlier about the fact that as you're building up an RNN, the state from earlier time steps end up getting diluted over time because we just keep feeding in behavior from the previous step in our run to the current step. And this can be a problem if you have a system where older behavior does not matter less than newer behavior. For example, if you're looking at words in a sentence, the words at the beginning of a sentence might even be more important than words toward the end. So if you're trying to learn the meaning of a sentence, the position of the word in the sentence, there is no inherent relationship between where that word is and how important it might be in many cases. So that's an example of where you might want to do something to counteract that effect. And one way to do that is something called the LSTM cell. It stands for long short-term memory cell. And the idea here is that it maintains separate ideas of both short-term and long-term states. And it does this in a fairly complex way. Now, fortunately, you don't really need to understand the nitty-gritty details of how it works. There is an image of it here for you to look at if you're curious. But the libraries that you use will implement this for you. The important thing to understand is that if you're dealing with a sequence of data where you don't want to give preferential treatment to more recent data, you probably want to use an LSTM cell instead of just using a straight-up RNN. There's also an optimization on top of LSTM cells called GRU cells. That stands for Gated Recurrent Unit. It's just a simplification on LSTM cells that performs almost as well. So if you need to strike a balance or a compromise between performance in the terms of how well your model works and performance in the terms of how long it takes to train it, a GRU cell might be a good choice. Training them is really hard. If you thought CNNs was hard, wait till you see RNNs. They are very sensitive to the topologies that you choose and the choice of hyperparameters. And since we have to simulate things over time and not just through, the static topology of your network, they can become extremely resource intensive. And if you make the wrong choices here, you might have a recurrent neural network that doesn't converge at all. It might be completely useless even after you've run it for hours to see if it actually works. So again, it's important to work upon previous research, try to find some sets of topologies and parameters that work well for similar problems to what you're trying to do. This all makes a lot more sense with an example, and you'll see that it's really nowhere near as hard as it sounds when you're using Keras. Now, I used to work at IMDb, so I can't resist using a movie-related example, so let's dive into that next and see RNNs, recurrent neural networks, in action.